Welcome back, Algebra 2 students. We are in Lesson 32. We're going to talk about the quotient theorem for square roots. We remember that the square root of a product can be written as the product of the square root of its factors. Thus, if we have 6, the square root of 6, we can write it as the square root of 3 and the square root of 2, right? Right next to each other. It means the same thing because this is understood to be multiplication. So also we can apply that to fractions. So when we have the square root of a fraction, we can turn that into the square root of this value over the square root of this value. So we can more easily access the parts of the fraction and still maintain the same value of the fraction. We don't want to change the value at all. Now remember, with fractions, let's say we have 1/2 as a fraction. We can increase this, like for instance when we need to find a common denominator, by multiplying both the top and the bottom by the same number, and we get 2/4. This is still the same value. It's still a half. It's just written differently. And we understand that it just is an unreduced half value. And if we reduce both of these by 2, we get back to the original value of the fraction. We can do the same thing with square roots in a fraction that we do without square roots in a fraction. And we want to do that for several reasons. One might be to make the problem easier to solve when we don't have a square root in the denominator. It might also be because we need to find a common denominator for this fraction, and it's in a problem, and we need to be able to build that relationship between another fraction and itself. So in order to do that, we do the same thing, but we use the square root that is in the bottom, that's in the denominator. So we say the square root of 3 times square root of 2, that gives us the square root of 6 over 2. Square root of 2 times square root of 2 is just 2. And that way we are able to eliminate the square root symbol, and it has a value now that we can manipulate and use in some type of calculation much more readily. But we know, because of this illustration here, that this is still the same value as this, because we multiplied both the top and the bottom by the same number. Okay, even though it's an irrational number, it's still the same number. And it makes the bottom a rational number that we can deal with. So understanding that, I would write this whole sample thing down here in your notes, and I would label it the quotient rule for radicals. And it's called the quotient rule because we know that a fraction is just a division problem, and the result of division is a quotient. All right, so I'm going to clear the page. Actually, I don't need to clear the page. For this first one, I'm just going to change colors. For 32.1, we have the square root of 3/7. So the first thing we do is we break that down into separate parts. The square root of 3 is the numerator, and the square root of 7 is the denominator. And now we're going to normalize the denominator and keep it from being an irrational number by multiplying both the top and the bottom by the square root of 7. So that's going to give us the square root of 21/7. And that's the answer for 32.1. Easy peasy. It's just straightforward multiplication. You just have to remember that this times this, you drop the radical sign. All right, it's the same thing that we would do up here. All right, let's try to do, I think we're going to need more room for 32.2, so we're going to clear the page. If you need to take more notes, pause. All right, 32.2. So we have the square root of 2 over 5 plus the square root of 5 over 2. And I like how they set this up for us so that we can see the numbers combine much more readily. It's a lot less work when the numbers are the same. So we're going to separate the first one into 2 and 5, both under the radical. And we're going to multiply both by the denominator of the square root of 5. And that gives us a result of the square root of 10 over 5. For the second number, I don't know what that did. I was pretty sure I wrote a 5. Okay, for the second number, we're going to separate that into the square root of 5 over the square root of 2. And we're going to multiply both of those by the denominator of the square root of 2, which gives us the square root of 10 over 2. So now we could put them together, and we could say the square root of 10 over 5 plus square root of 10 over 2. But we can't add them together because the denominators are different. So now we have to treat the denominators like we normally would and multiply each by the other, and then we will have something that we can add together. So when we multiply this fraction by 2, it looks like this. 2 times the square root of 10 over 10, because 2 times 5 is 10. And when we multiply this fraction, we get 5 times the square root of 10 over 10, because 5 times 2 is 10. Now that we have the same denominator and we also have the same radical, we can add these together, and we get 7 times the square root of 10 over 10. Okay? So there's a little bit of pre-work to be done, and then you have to get the same denominator, and then you can do the addition. All right? So the first thing we have to do, the steps are to separate, should be an A, separate the numerator and the denominator into separate radicals. Or you could just say into radicals, individual radicals. And radical is just another word for the square root symbol. The second step is to multiply each fraction by its denominator. The third step is going to be to then find a common denominator and finally to solve. Right? And those are your 4 steps for handling this type of a problem. So let's do 32.3. You could finish writing this down in your notebook. Pause if you need to. I am clearing the page. So let's move on and let's do 32.3. In this one, we have a constant in front of our square rooted fraction. This is 32.3. And this is 7 over 3. Again, they've just flipped the fractions for us to make it easy. So we're going to separate these, and when we do, the constant goes up with the numerator. So 3 times square root of 3 over the square root of 7. And we're going to multiply that by the square root of 7. And that is going to give us 3 times the square root of 21 over 7 for the first fraction. For the second fraction, we do the same thing. 5 times the square root of 7 over the square root of 3. Multiply all of that by the square root of 3. And that's going to equal 5 times the square root of 21 over 3. Now we need to make these each have the same common denominator, and we'll do that by multiplying each by the opposite denominator. So we'll multiply this fraction by 3, so we end up with 9 times the square root of 21 over 21, and the operation between the two was minus. Don't forget about that. And don't forget which one is which one came first and which one came second, because that can affect the value of your answer. So now we multiply the second fraction by 7, and we end up with 35 times the square root of 21 over 21. Now that they have the same denominator, and because they both have the same radical, we can subtract the constants. So 9 minus 35 is going to be negative 26 times the square root of 21 over 21. All right. If you have any questions about this, this is a good time. Write them in your notebook, and then when you come to class, you can bring those questions to me. You can say, okay, I didn't understand this about this. So anytime you have a question in class, or you have a question during a lesson, you can either write it down and bring it to class, or you can message me about it, and I can answer it as quickly as possible. So let's clear 32.3 and do 32.4. Yes, that's supposed to be a 4. I know it doesn't. There we go. That's a little bit better. This pen is not the easiest to work with. Plus, my handwriting is not that great. So we're going to simplify this problem. We have 2 times the square root of 2 over 7 minus 5 times the square root of 7 over 2. And again, we do the same thing. We put this up here with this, and we put the 7 as the denominator. I'm going to save a little bit of time this time, and I'm just going to write it together. And then I'm going to do most of this in my head. I'm going to turn this into 2 times the square root of 14 over 7 minus 5 times the square root of 14 over 2. And then I'm going to multiply again, and that's going to be 4 times the square root of 14 over 14 minus 35 times the square root of 14 over 14. And that is going to equal a negative 31 times the square root of 14 over 14. And you can see how easy these are to do. Once you get into the pattern and into the practice of doing them, they're the same thing over and over again. Okay? They've given us some easy numbers to work with so that the radicals end up being the same and we can actually perform the math. If the radicals are not the same, then you're stuck. You have to just stop where you are. Even if you go and get the same numerator, or I'm sorry, the same denominator, If the radicals are not the same, you can't do the same math, because these radicals, as we've said before, you treat your radical or your square root as if it's a variable, and it has to match. You wouldn't add 4x to 35y. They'd have to be the same variable in order for you to complete that. So the number under the radical has to be the same in order for you to do the math. All right, that's all that I have for 32A, talking about the quotient rule. Now we're going to move on to 32B and talk about congruency. Let me clear the page. In mathematics, we understand that only numbers are actually equal. Everything else is just congruent. So when we have a line here, let's say we have this line here, right? And I'm going to put a point here and a point here, this line segment. This is AB, and it's 4. And let's say I have another line right under it. It's exactly, we'll pretend, I don't know if it is or not. We'll say it's exactly the same length. It's 4. We don't say that AB and CD are equal. We say that line AB is congruent to line CD, because they're shapes, they're not values. Now, if you said the measure of line AB is equal to the measure of line CD, then you'd be correct. But shapes can only be congruent to one another, whereas numbers in math can only be equal. Right, so keep that in mind whenever you are writing statements about triangles or shapes or polygons being alike. They're congruent, they're not equal. And that's okay. If you notice this little mark above the equal sign that makes it a congruent symbol, that's a tilde. And a tilde means approximately. So this congruence symbol literally means it's pretty much the same, right? It means it's pretty much the same. So it has the same weight as being equal, but we try not to say shapes are equal because we don't measure them per se. So if I have the notation is read when we have this, that AB is equal to CD. And the notation uses a symbol for congruency, and it's read that AB is congruent to CD. The numbers used to describe the measures of the angles here also, we have this one, and it's 37 degrees, and we have another one just like it. Try to do my best to make it just like it. This one says it's 37 degrees too. We can again say that the measure of the angles, whatever this first angle number 1, angle number 2, angle number 1, is equal to the measure of angle number 2. But we can't say that angle 1 is equal to angle 2. Instead, we have to say they are congruent. So it's all about the wording. When you use this symbol, then you have to use the right equality statement for it. It's a geometric equality statement, and we never use that with shapes, only with measurement, only with numbers. All right. Thus we see that congruent is a word that means geometrically equal. Not mathematically equal, but geometrically equal. All right. That being said, let's look at a statement of congruency. We're careful. I'm going to erase all of this right here. we're careful. Let's say we have two of these triangles here. And technically, these triangles let's say for all intents and purposes that they have the same hypotenuse, the same two legs, the same degrees of measure, everything is the same. When we write the statement of congruency, we make sure that we list vertices whose angles are equal in the same order. So if this were A, B, and C, and this was D, E, and F, we have to be careful to make sure that we put the angles in the right order. So if we were to say triangle ABC is congruent to this other triangle, we'd have to make sure we start with the right triangle. So A is the short side next to B, right here. So we would start with F, then we move to E, and then we go to the long side D. So we have to put them in the same order, or they're not congruent. It matters. Okay? Sometimes it's necessary to flip a triangle to make it fit. And we call that a reflection about a line. Congruent triangles, like these we have here, are similar triangles whose scale factor is 1. So they are direct reflection or a direct copy, so to speak, of the original triangle. That's what makes them congruent, is because they're the same scale. They're not similar triangles. Similar triangles are going to be triangles that have a scale factor where the length was just increased by the same amount all the way around. That's not what a congruent triangle. A congruent triangle is triangles that have the same length of legs, the same degree measure on the inside, the same hypotenuse. They're all the same. So let me give you a problem here. Let's see if I can do this. 32.5 is the example number. And I'm going to give you a pair. I think I could do this pretty easily. All right, here's this triangle. Boom. Oh, perfect. I'm going to copy it. And I'm going to paste it. All right, so we have two triangles that we know are exactly alike, right? So let me label them for us. I need to have a pen, obviously. This is going to be 4x plus 1. This one is 6x plus 2. This one is 6. This one is p. This one is 6. And this is 12x minus 4. Now, this angle is congruent to this angle. And this angle is congruent to this angle because they are direct copies. We know they're the same angle. And we're told to find x and p. That's what we have to do. So we remember that if two angles are equal, the third angles are equal also. So the triangles are similar by the AAA theorem. The sides opposite the tick marked angles are both 6 units long. This is 6 and this is 6. And these triangles are congruent because the scale factor is 1. Because a pair of corresponding sides have equal lengths, we add the letter S to the AAA and say that the triangles are congruent by AAAS. Thus, the sides opposite the double tick mark angles also have equal lengths. That's a bunch of geometry talk, and we really haven't talked about that so far in Algebra 2, so we're starting to get into some of the geometry theorems and axioms. That's okay. We don't need to memorize those. Basically, what you need to understand geometry is common sense. We know that if we have two angles that are the same and they have an adjacent side that is the same, that these are going to be congruent triangles. So we can just make our little congruent symbol here. These two are congruent to one another. If they weren't congruent to one another, we couldn't find x and we couldn't find p. So let's do that now. Let's find x and find p. So first we have to find x. So we know these two are equal to one another. So we can set those here, 6x plus 2. If my pen wants to work tonight. And that's going to equal 12x minus 4. And yes, we could say equal because this is math. It's not a shape. This is a shape, but this is math. All right, so we're going to add 4 to both sides, just because I can. And that's going to be 6 here, and we're going to subtract 6x from both sides. So this cancels and this cancels, and this becomes 6 is equal to 6x. So x is equal to 1, right? Alrighty then, so 1 is the measure of x. Now we can find what p is because we know what the value of x is, and we know that 4x plus 1 is congruent or is equal to p. So we'll find that. 4x plus 1 equals p. We know that x is 1, so 4 times 1 is 4. 4 plus 1 is 5 is the measure of p. All right, so that wasn't too difficult. That's really what we're going to be dealing with when we're talking about congruent triangles. We're going to be asked to find, just like when we were doing the angles, we had to find the value of this and the value of that. It's all about knowing where to start. And what you do is you're going to look for those sides or those locations on the congruent triangles that have the same variable, because when they have the same variable, then you can solve for it by setting them equal to one another. There's no way we could have started with 4x plus 1 equals p. We couldn't have done that because when you have two variables, there's too much that can be changed. Like this could have way more implications than just a one variable problem. So that's just like when we do substitution so we can have just one variable that we can solve for. So look for that. Look for the place to start as the ones that you can compare that only have the one variable, that have the same variable in both parts. All right, I think I've harped on that enough. That's all I have for lesson 32. Don't forget to do the practice problems, and if you have questions, write them down, bring them to class, or message me and I'll answer them as soon as possible. Again, on Sunday morning specifically, I usually am not going to look at my phone. In fact, it's usually on silent all day Sunday because we go to church. So if you send me something on Sunday morning, I'm probably not going to see it until that afternoon. Okay, just FYI. I'll see you guys in class and in lesson 33.